Okay. Hello, everyone. My name is Paul Townend. I can't see myself or you guys, so please bear with me in this. So I'm going to present just a very high-level view of just some of the scientific contributions of COGNIT, because we've done a lot of work during the course of this project. Now, I haven't been able to see the other presentations this morning, so I apologize if I repeat some of what they've said, but I'm going to start very, very quickly, just recapping what do we mean by serverless in the context of COGNIT. So essentially, serverless is just abstracting infrastructure away from the application and to the provider. So in other words, as a company, as an industry, if we develop a function or we develop some kind of code, we can send it to the cloud and the cloud will manage it for us. We don't have to think about those servers. And so it's really great for users. We don't have to have all of the staff training to actually manage scaling of applications or placement of applications, anything like that. It's a little bit more challenging for providers because obviously the providers now have to do all of that work themselves. So the purpose of COGNIT, one of the major purposes of COGNIT, is to develop an open source framework and implementation to enable serverless to be used and simplify deployments primarily for developers and SMEs. And this is obviously under the context of digital sovereignty. So by developing this framework, by developing this technology, Europeans or anyone for that matter can quickly deploy a serverless framework which will enable their customers to use their services in a very simple way. So there's a lot of challenges when we think about serverless in the context of a cloud continuum. So obviously there's a lot of management going on because we've got different clusters across a wide area. So we have to think about, we've got a highly distributed system, everything's disaggregated, there might be software-defined networks. There's all kinds of extra infrastructure that we have to consider. We've got to decide where do we actually, how do we deploy a function? How do we migrate a function across that distributed infrastructure? We've got to think, how do we actually allow users to seamlessly access this very distributed system with lots of different clusters? We've got to think about, in addition to all of that, especially at scale, how do we keep everything secure? How do we keep everything trusted? We've got to think about potentially new types of serverless functions. So in the past, serverless functions have been very, very short-lived. But what if we want to do something that takes a longer amount of time, for example? What if we want to be more aware of where we're running that serverless function to reduce latency, for example? And we want to keep everything energy and carbon efficient. That's particularly key now because, as you've probably seen from headlines, AI is just burning through the environment. It's consuming massive amounts of power. It's consuming huge amounts of water as well. So we want to be able to do all of this, but do it in a very energy efficient, carbon efficient way. Keep everything as sustainable as we can. And to do all of this, we really need AI models and optimization techniques to manage all of this, to ensure all of this is possible. And that's where COGNIT comes in. So COGNIT has 6 different objectives. Antonio may have covered some of these. So I'm just going to take a few of them, and I'm going to show you a few of the things that we've done in those areas and give you a flavor of the project. And obviously, if I touch on something that's really interesting, you can talk to us and we can give you a lot more information about what the project has actually done. So I'm going to start with Objective 1. Objective 1 is the definition of a serverless framework architecture with AI-enabled disaggregated management. In other words, one of the central objectives of this project, and I'm sure you've seen some of this with Antonio, is to create an open source architecture that shows us how do we actually do serverless in a continuum with AI management. And this is a key part of European digital sovereignty. We need this kind of architecture available to us because we do not want to rely on the hyperscalers in, for example, the US, which is increasingly a problem for industry. We want to have a European solution to this, and this is where COGNIT's really coming in. So this is a view of the COGNIT architecture. And I will take you through how this works very briefly. But essentially, in the top left, we've got this brown box at the device client. So you could have a low power device. You could have a laptop or some kind of embedded system that wants to offload functionality to the cloud. That's a key part of what we want to do with COGNIT. So the device client actually has an API. It has a small piece of code, very low memory, that it gets from the COGNIT library, and it allows that device to connect to the COGNIT front end, which you see in the middle of the screen near the top, the COGNIT front end. And the COGNIT front end essentially allows a device client to authenticate. So we're keeping secure, end-to-end security in this system. We can authenticate through the front end and get a token back, which we can then use to connect to all of the other components within COGNIT. And then once the device client's authenticated, it can upload its requirements and upload its function, what code it wants to execute, to the front end. And then the front end will connect with the AI orchestrator, and the AI orchestrator, which is the brain of COGNIT. We'll talk more about that shortly. The AI orchestrator is going to be able to look at those requirements and decide where is the right place in the continuum for this device to connect to perform its functions. And so the device client will send this back through the front end. The device client can then connect directly to that particular edge cluster, that particular part of the continuum, and that it can then run its functions. And through the Cloud Edge Manager and that edge cluster front end, we can help that device client by scaling up and down and load balancing those requests as necessary. And that's really at a very, very high level what COGNIT is doing from an architectural perspective. Obviously, there's a lot more detail on that. I'll show you a little bit more shortly. But the AI orchestrator, as I say, is the brain of this. And it's something we've spent a lot of time and resource on. We've got a lot of different components within that orchestrator, and I will give you a flavor. I don't have time to go through all of it. I'll give you a flavor shortly of what that orchestrator is actually doing, or some of the scientific contributions we've made through that. But here, as you can see, just again, is what I've explained already. This, you can look at this later. It's a sequence diagram showing how all of the different components within our architecture connect and what the path through that system is. But as you can see, devices connect to the front end, which connects to the Cloud Edge Manager and gives you a token. You can then access the whole of the COGNIT system. You upload your requirements and your functions, and then through our AI-enabled orchestration mechanisms, we can tell you exactly where. We can give you an endpoint and tell you exactly where to run those functions, and then we will manage everything else for you. So it's a really, really nice architecture and system. So that we've fulfilled objective 1 of this project. Objective 2 is developing a new paradigm based on FAST that provides access to the cloud. And essentially, that's the open source serverless runtime. You'll hear more about this later, so I'm really not going to go into the runtimes themselves during my presentation. All you really need to know is that we've developed a serverless runtime. So that's something that runs your function, that supports multiple different languages, primarily C and Python. It exposes information about the function execution that allows our AI orchestration mechanisms to monitor and manage the functions. There's a full API available And everything is fully secure via Biscuit tokens. So there's end-to-end security in this system. And a real key point here is the COGNIT serverless runtime is very low memory footprint. So you can add this and deploy this on devices that are otherwise very resource constrained. You can read more about that in one of our many publications, and you'll hear more about this later. So really, I want to talk more about Objective 3, and that's and Objective 4, which is to essentially develop this AI orchestration for the system. So we've done a lot of different work in the AI, in the context of AI in Cognit. We've developed a set what we call formal models for the cloud edge continuum. So we've thought a lot, and we've developed a lot of mathematical models that allow the AI to reason across an entire continuum. So from the devices to the clusters, the locations, even the energy providers that those locations have. And by having those models, we can start applying novel algorithms and scheduling mechanisms to make our system more efficient, to make it more performant, to ensure its security and its trustworthiness. We've looked at a lot of approaches to actually classifying workloads. So when you're submitting jobs, we need to understand roughly what the job or what the function is doing in some way in order to make it more efficient. And I'll show you very briefly how we've done that in a bit. We've developed mechanisms to monitor and optimize continuously across this system. And we've even got a library of different AI models that we've trained that you can select from as necessary to fulfill your needs. And again, you can read about this in one of our many publications. So those learning models I mentioned, I'm not going to go into detail because I know most of us are not, we know what AI is, but we're not really necessarily interested in the hard math or the hard algorithms behind this. But essentially, workloads that Cognit is considering are typically unlabeled. We need to learn how they're working without any real formal knowledge of them. And so we've spent a lot of time looking at, well, what are the existing mechanisms that we could use to cluster, to classify those different types of workloads, and what the limitations of those? How can we progress them and develop them further? So this diagram is just to look pretty. It's not actually, you're not supposed to learn anything from this. But essentially, we looked at two different forms of clustering, a traditional one called k-means clustering, which some of you may have heard of. But essentially, that takes a couple of parameters and clusters workloads based on certain characteristics. But then we realized that this is not giving us a really clear picture of what's going on. So we've developed what we call we're using what we call deep k-means. So essentially, we're using some AI techniques called autoencoders to actually reduce the amount of data we're looking at from an AI perspective. And then we apply k-means to that reduced representation of the system. And it gives us much more clear understanding and a clear-cut separation of the different types of workload in the system. So that's one of our, and we can do all of this without talking to the user. So this is an unsupervised approach, which is showing clear progression over the state of the art. And we've also developed, like I mentioned earlier, these models that can reason across multiple clusters. So we've developed a lot of work which looks at what are the different components and their interactions in a continuum. How can we reason across those interactions and components and develop new scheduling mechanisms, new approaches to actually exploit these multiple clusters, and in order to allow our users to get the most optimum results possible through the AI. And we've looked at a lot of different types of algorithms. We've looked at a lot of different ways of reducing energy consumption, for example, reducing carbon consumption, keeping performance as high as possible. And we can actually vary it depending on what algorithms and choices we make based on the requirements. We can actually place things in a way that could allow us to, for example, maximize performance or reduce rather the amount of energy being used, or reduce the carbon footprint of the system. So we've got lots of different options, and all of these are available through the project. And we've also done a lot of work, like I said, one of the hot topics right now is power and carbon. We want to make sure that what we're doing with AI in Cognit is going to be very sustainable. It's going to be something that's going to try and reduce, or at least manage, this huge amount of power that AI is consuming currently. And we've done a huge amount of work in this space. Again, we've got those formal models. We're looking at what we call stable matching approaches for scheduling. We're looking at server profile approaches. So I'll take you through some of those briefly. So imagine you've got some data centers in a region, and we've got a lot of edge clusters in that region too. So like we know, one of the things that Cognit does is where should we place a function in order to maximize performance, minimize carbon. Well, if you view it from a continuum perspective, those regions all have different power providers, different carbon footprints, different cluster profiles, different server profiles. So we've built up models that can manage all of this. We've also looked at work. So we've just been published actually in IEEE CloudCom a couple of weeks ago, talking in depth about this and looking at some of the different AI approaches we have to minimizing, for example, carbon in a system like this. And one other thing I'd like to mention, because I'm almost out of time, is some work we've actually done. It's actually attracted the attention of Intel in Germany. So don't worry, we're still European. But essentially, we can also now, we've got the ability to reason across clusters where some of the machines might be in low power mode. So at the moment, traditional schedulers assume everything in a cluster is kind of homogeneous. It looks the same. But now we've got the ability to actually set the BIOS and some of those server machines to be low power. So DVFS, if you know what that is. Machines may be running at half the power of the other machines. They run slower, but they consume less power, and that reduces operational expenditure. Well, we can now actually detect which of those machines are in low power mode, which of the machines are in high performance mode. And based on the user requirements, we can again schedule within that cluster using the AI in order to make sure that we meet all of our user requirements, while also wherever possible running things in low power mode. So we can, and in our initial tests, we actually reduced cluster power by 12% and still maintained all user requirements. And that's just our first work in this area. And as I say, this work has attracted the attention of Intel. So it's really, really state of the art. Again, this was published a couple of weeks ago now. So I'm just giving you a flavor of a few of the things we've done in Cognit. And you've heard from Antonio about the use cases that Cognit has that's using some of this AI technology. And you'll hear more about that, I believe, later today. So in summary, I would say that just a few of our many scientific contributions, and we've got an open source architecture and implementation for doing this. You can take this technology and apply it to your own systems. It's all available to you. We've got a low memory footprint, multi-language serverless runtime, so we can deploy this on devices that are quite constrained in power and size. We've got an open source AI orchestration mechanism with all of those models I told you about and all of the technologies I've mentioned. We can classify workloads. We can do stable matching approaches to basically complicated mathematical ways of distributing functions around a continuum. We can even consider the power profiles of servers now. And as we've mentioned, this is going to be validated through the use cases. So that's all I'm going to say today, but thank you very much. We've got a lot of work. You can contact me at any time if you want more information. We have many, many papers, many different approaches to doing this, but we're really proud of our architecture. We're really proud of the serverless runtime. We're really proud of the AI. And also, just the contribution we're making to trying to lower the energy and carbon footprint of AI in European systems. Okay, that's my 20 minutes. Thank you. I don't know how to stop this.